So for this example, we're going to look, or this section, we're going to look at graphing rational functions. So we've done everything so far. We've done everything with rational functions. Now we have to put it all together. Who can tell me what are the things that we've done so far? What have we done so far with rational functions? Give me one piece. Asymptotes. Next. Holes. Erickson. Intercepts. Say again?
The graph itself.
We haven't yet. We've looked on the calculator, but now we're going to graph. So let's say calculator graph. And behavior, like the asymptotes, like slant and horizontal. Okay, and then the last thing we're going to do is use points if necessary. So it's really simple. All I said was just AHIP. Asymptotes include end behavior. Because remember, slant and horizontal asymptotes are really end behavior. But we also have to look at vertical asymptotes. Holes and intercepts, okay, along the graph. And then points. What are the points going to be useful for? Why would we need more points besides what we do? Yeah, to show the connection of the points. But the asymptotes are going to give us boundaries. So, if you had, and you can write this on the side actually, write it right on the side here. If you had this, how would you think those points would connect if you had 4 points like that? How would you think they would connect, honestly? Straight line, right? Would everybody agree? Okay? But now, if you knew it was a rational function, and you knew there was a vertical asymptote here, they might actually look like this. Do you see how crazy that is? 2 points, you think it's a line, but if there was a vertical asymptote on the y-axis, they would probably look like that actually, because they can't cross the vertical asymptote. So the points are not enough with rational functions. So step 4 here, points on curve, are not enough. That's why we did the first 3 things. Is that clear? I want you to know why we're actually going through these parts. If you just plot points, you don't really know how it's going to look. The asymptotes, though, dictate some of the behavior. Okay. With that said, let's go to number 1. We have to do all these for every number. For every question, we're going to do all of the steps. So looking at number 1. Easiest way to start any of these problems is to factor. So I'm going to tell you right now, factor every time. Okay? Factor every time. So that's what you get for m of x there when we factor it. Now, do any factors repeat? So there's no holes. I'm going to go ahead and do this. Okay? So I put an x next to it to tell me that I've done it and it doesn't even apply. Asymptotes. Are there any vertical asymptotes? If so, where are they? Or what are their equations? Yeah, 1 and -1. Remember, the denominator gives you vertical asymptotes. The numerator gives you the zeros. That's the easy way to remember this always. Okay? So the denominator you get, 1 and -1. But take a look, please, write it this way. Because it's an equation of a line. It's a vertical line. So asymptotes we're good on. But now what about slant or horizontal asymptote? What do we have for degrees? Look at the original function. What's the degree of the numerator?
1.
Not denominator. So the numerator is less than the denominator. Agreed? So we start with this. Since the degree of the numerator is less than the denominator, what do we have? What is it? Yeah, y equals 0. Be careful. Again, we have a horizontal asymptote of y equals 0. It's an equation. So this is this part here. So let's circle this, and this so far. So we're done with asymptotes. What did I say? If you have horizontal, you can't have slant. So once you get the fact that it's a horizontal, don't even worry about checking for slant, because that would come about if the degree of the numerator were greater than the degree of the denominator. So we're done with asymptotes, we're done with holes. Last part, pretty easy, right? Intercepts. How do you find the y-intercept? Look at the... Okay, that works, but just look at the ratio of the constants, remember? What's the constant up top? And what's 0 over -1? It's still 0, right? Take a look here. If you plug in 0 for x, you get 0 over -1. Same thing. So the y-intercept is 0. Huh, that's kind of funny, isn't it? What's the x value when we're looking at the y-intercept? What is it? So what's the coordinate? 0, 0, right? It's 0, 0, which is kind of, all right, that's kind of weird, right? Because now look, that's what we get for the y-intercept. Again, setting x to 0, or just looking at the ratio of the constants. If that's the y-intercept, what else is it? Yeah, the x-intercept occurs when y equals 0. Well, take a look. Both x and y equals 0. What is this called again? 0, 0? The origin. And the origin is both an x and y-intercept. How do you check that? Well, look at the x-intercept. Remember what we do? Set y equal to 0. If you set y equal to 0, and take a look like we talked about yesterday, just set the numerator equal to 0. That's what gives you the zeros. Well, doing that, what do you get? 0, 0. Same thing. Okay? These are the same for that reason. Okay? Again, these are the same because they're both x and y-intercepts at the same time. So there's only one x-intercept, and it happens to also be the y-intercept. So what I want to look at now is the idea of what this looks like before we start to pick points. So you can see what I'm talking about. So take a look. Oops. Yes. Take a look at the original graph, please, at the top right. That's what we have so far. I'm going to highlight stuff and you tell me what I'm talking about. Okay? What does this represent right here? Manny, which one? And what is its equation? Very good, Manny. What is this one then, Manny, since you did that? Good. So those are the vertical asymptotes. Mike, what's this red line going across the x-axis? You can barely see. Yes, and why is it a dashed red line on top of it? You can't see it on yours, so look up, Mike. I'm showing you here. There's a little dashed red line that sits on top of the x-axis. Why is that line there? What boundary is it? Help him out, Summer. Not the x-intercept. Katerina? The horizontal asymptote, y equals 0. Remember there was a horizontal asymptote, and it was at y equals 0. Make sense, Mike? Okay, go back and look at the previous page we saw for the horizontal asymptote. What is this here? This is the x and the y-intercept. That's all we know. Is that enough to graph? It clearly isn't, because you can already see the answer down at the bottom here. So what do we do? Here's what we do. Write this down, please. Pick points around the discontinuities, or the vertical asymptotes, really. Pick points around the vertical asymptotes. So notice what I did on my table. Take a look over here, please. I realized that in between the vertical asymptotes, I don't have much room. I have room between -1 and 1. So I need to plot some points in here. So I should pick fractions. What fractions did I choose? I chose fractions like 1/2, 3/4, 1.5 outside of there. So that's going back here to -1.5, then back to 2, and then back to -3. So what I did was I chose values that assisted in my graphing, and I picked decimals here because I needed to get in between here. Those are all those ones in the middle, all these decimals in the middle. Then outside, the 1.5, 2, and 3, 1.5, 2, and 3, I chose on the right and the left. I chose symmetric numbers because I saw symmetry in the graph. Do you all see symmetry in this graph already up top? Okay, that's why I chose numbers that were symmetric. But you don't have to do that. So if you only have one vertical asymptote, it's at 4, you could choose like 3, 2, -1, -3, and then like 5, 6, 7. Okay? But you're picking numbers around the vertical asymptotes to help plot. Use your table function on your calculator. Don't go through the math on this by hand. It really isn't worth it. Does that make sense? Yes? Yes?
How many points should you pick on each?
Every problem is different. Yeah. For the most part, if you have a boundary where there's a region in between, at least 4 or 5 points evenly spaced. Outside, 3 or 4 each side, maybe. But we can have 4 vertical asymptotes, and then we have some craziness going down.
Wait, how come you even need to graph
You should do it on the calculator, but if you're going to graph by hand, right, Danny? This part you know from what you've gathered in data, you need actual points. You can't just...
Why would you just need a graph by hand if you could just do it on the calculator?
Because on the test, when I say, can you show me that you can graph this, how are you going to show me? You know what I mean? I want you to actually graph this in practice.
In real life, you never do by hand.
Depends, really. You could, if you're plotting data and you're looking at quick sketches. You need to know what shapes look like. So by doing it by hand, it helps you recall those shapes later in life, so that if you're using some sort of program, you can make sense of it. So if you're graphing a calculator and you're graphing a rational function, and you got something that looked like a line, you would clearly know you made a mistake, right? Or there's something weird going on there. So the idea of the trends and what they look like, that's what we're trying to get through here. Becoming familiar with these types of functions and their behavior. All right. Let's go on to So for this example, we're going to see the numerator factors in x minus 3x plus 3. And the denominator doesn't factor. So right away we see there's no holes because nothing cancels. But setting the denominator equal to 0, we're going to see that this becomes a negative number. So we're going to have a negative under a radical, which means that the vertical asymptotes would be imaginary, so there are none. The horizontal asymptote, we can see right away, since the degrees are equal, is just a ratio of the leading coefficients. So it's 1 over 2, or 1/2. The y-intercept, setting x to 0, or looking at the constants, we're going to see is negative 9 over 1, or 0 comma negative 9. The x-intercepts come from setting the numerator equal to 0, so we get 3 and negative 3. Then we draw a mental sketch of this, and what we're going to see right away is that we have symmetry here. We don't have much else. Symmetry here with these two numbers. So points we may pick are numbers in here. Okay, so 1, 2, 1, negative 2, maybe outside, or some decimals. So using these points, we're going to see the graph here. Now we'll notice that the horizontal asymptote is on both ends the same, so both ends are going toward it. There's no vertical asymptote here at all. And here's our y-intercept, and these are our x-intercepts. So what we're going to notice is when we look at our graph of this one, okay, after looking at all the evidence, any questions, by the way, on the other stuff? Did it all make sense when you read through this? Yes? All right. But when we look at our graph here, what we're going to notice is that we have this odd-looking graph, right? Very different than anything we've seen so far, because now we have a slant asymptote. We've got these 3 points here. Okay, the x-intercepts and the y-intercept, which honestly, they look out of place. It doesn't look like it makes much sense, right? Just by looking at this. I don't know what's going on. I don't know what's really happening. We have this vertical and slant asymptote. So this is an example where, again, points are very much needed. Now, here's your vertical asymptote. So what points might you pick for this one? Give me a suggestion. 3. What else? What other x values for your table? 4. Maybe 5, okay. All right, and what about on this side? What would you pick?
Negative 2, negative 3, negative 4.
Agreed, okay? So again, you're just going left and right, not too far in each direction. In doing so, yeah, the vertical asymptote. In doing so, this is what we actually get. And it's a little bit different because I changed the zoom on the graph, obviously. But this is what you end up getting. You get this little curve in here, this little loop, and the same thing up here. And that's what we're seeing down here at the bottom right here. Okay? It's an interesting looking rational function. What it is, it's actually called, in this case, that would be like a hyperbola. Hyperbola. Okay? Hyperbola. It's kind of the opposite of an ellipse. Imagine if you took an ellipse. You know what an ellipse is or no? What is that? Anybody see that, sir? Weird. Alright, if you took an ellipse and cut it down the middle, and then literally opened it up. See, that's what it would become? So cut it down the middle and unfold it open. Isn't that what you get? These two curves like that? That's what this is right here. Okay? So if you took an ellipse, cut it down the middle, and just open it up like that. You gotta whistle when you do it too, okay? Open it up, put it like that, you have a hyperbola. That's the shape. Okay. Any questions? Alright. Finally, an example with a hole in it. So we start by factoring. We've got our numerator and denominator. We see that x minus, or x equals negative 7 is clearly a hole. So we have to simplify the function. So we go ahead and we simplify the function here. Then, to find the location of the hole, you take what would make it a hole, which is negative 7, and plug it into the simplified function here. So plug in negative 7 in these two spots, you get negative 11 over negative 9. And I'm going to write that as a decimal, always, because it helps me plot, okay? So the whole is negative 7, 1.2 repeating. There's only a vertical asymptote at x equals 2, because this is what's left over right here. This x minus 2. Since the degree of the numerator is the same as the denominator, we look at the ratio of the leading coefficients, which is really 1 over 1. So it's just y equals 1. To find the y-intercept, we set x to 0, or just look at these two. What's the ratio of these? Just simply 2. To find the x-intercepts, we have to remember we have two x-intercepts up top, but what's the big deal here? How is this different than the last ones? One of them is a whole. So the only x-intercept comes from x minus 4, which makes the only x-intercept 4, comma, 0. Here's what we've got as a graph so far. It is completely pointless, right? Does this help at all? Graph does nothing really. So you have your boundaries though at least, and now we have to pick our points accordingly. So we pick to the left and right of the value positive 2, since that's our vertical asymptote. Picking values, plotting them, we see we still have another shape that looks very much like a hyperbola. Again. Say again? Oh. Anyhow. Does that make sense, right? Is this pretty easy after a while? Do you see now? And I know, remember the other day I said, trust me, we're going to do all this at once, and you're going to see how they all go together. This is kind of the culmination of the last 3 lessons. Okay? Example 5. We've got 2 more to go here. 2 more to go. Or maybe 3. There's 2 on this page. Alright, example 5 is very interesting. And I started by saying this is a very interesting problem. It really is. The reason being is when you factor the numerator, jump right to here, please. When you factor the numerator, you see right away that the x plus 4 is canceled. Can you make this a little bigger? Really? That happens from time to time. It's like a little bit of a bug. Hold on. Alright, well, for now. The idea, though, is that you have the same factor in the top and the bottom, which is obviously going to tell us that there must be a hole, right? So there's a hole at x equals negative 4. Now, if you simplify this, all you're left with is x minus 3. Does everybody see that? That's all you're left with, x minus 3. And if you evaluate the hole, so if we put negative 4 into the simplified form here, what do you get when you do negative 4 minus 3? Yeah, so the hole is negative 4, negative 7. That's right here on the graph. Everybody see that? Okay, it's right there on the graph there. Now, the thing is this. If you try to graph the rest of this, because there's nothing else to do here. There's no vertical asymptotes. There's only one root, and it's at 3, and that's plotted right there. But if you graph something like this, it's a line, because the simplified form is just a line. Look at the simplified form. Everybody see it was x minus 3? This is the graph of x minus 3. That's all it is. So let's write down a statement here. If the simplified form is linear, then you have a line only with a hole in it. If the simplified form ever turns out to be linear, you have a line and you only have a hole in it. That's all you need to worry about. Yeah. There wouldn't be any. No, because horizontal asymptotes exist when you have a ratio of a denominator equal to the numerator or numerator less than the denominator, right? What is this? This would be a slant asymptote. But when you do long division, you're just going to get x minus 3. So the slant asymptote is the line. So you do have a slant asymptote if you want to solve. Sure you could. You can do that. That's fine. Use synthetic if you want. But the slant asymptote is the actual graph. Okay? Good question. I do not know what's going on with the notes here, guys. Something's bugging out the program today, so bear with me. Big empty white box on the screen. But you have it on your paper. So for this example, oops, over the top a little bit. We start by factoring. Okay, we take a look, we say, okay, there's clearly no holes in this problem, but we have 2 vertical asymptotes, x equals 3 and x equals 0. X equals 0, you notice, what did I put in parentheses? What is that really? What's the line x equals 0? Yeah, it's the y-axis. So we've got a vertical asymptote on the y-axis and at 3. Here's the y-axis vertical asymptote that you can't really see. Then the y-intercept. Why does the y-intercept not exist here? I know it says it already, but tell me in your own words. Why does it make sense?
Because it's 4 over, negative 4 over 0.
Yeah, or if you just look at the denominator, there's no constant, right? The denominator's constant is really 0. So anything over 0 is undefined, so there's no y-intercept. But the x-intercept is clearly 4, because you set the numerator equal to 0 to get that, and you get 4. So there is no y-intercept. I'm going to draw the rest of this axis. Okay. Why is the horizontal asymptote on the x-axis? Why is the horizontal asymptote on the x-axis? Nobody really? I mean, it says it, or you know it, I hope. Jules? What? But why is it y equals 0? We didn't make that statement yet.
The degree of the numerator is less than
Good. Very good, Jules. When the degree of the numerator is less than the denominator, we have a horizontal asymptote at y equals 0, so it's on the x-axis. So we've got asymptotes on our x and y-axis. Okay, on our x and our y-axis, which is kind of interesting to think about. So in this kind of a problem, even though we have an x-intercept over here, it's only because, what did we say? You can cross horizontal asymptotes, which is why you still have an x-intercept at 4, 0. Because you can cross horizontal, but can you cross vertical asymptotes? No, because it's a domain restriction. That's why they're different. So we make a table of values, and take a look at this graph. This is a weird looking one, isn't it? We chose values to the left of 0, choosing -0.5, -1, -2, -4. On the right, we choose numbers between 0 and 3. And on the right of the right asymptote, we choose numbers to the right of 3. Okay? Any questions? Could you do this on your own, you think? Yes, I hope? No? You don't think so yet? There's a lot to do, but just remember AHIP every time. Asymptotes and end behavior, holes, intercepts, and points. If you do that every time, you're bound to get the right answer. Okay? Alejandro, you have a question? Okay. I think we have one more, right? One more? Oh, this is my favorite one. Forgot about this one. So, can you guys do me a favor? Can you not look at the answer? Is that possible? Can you cover it up? Use another piece of paper and cover up the answer? So just have a problem over there? Thank you. Alright. So, I'm going to go like this. Okay? So I want you to actually do this. I don't want you to see my answer for this one. I want you to actually do it. Okay? And I want you to think about it as we go through it. And I'm going to talk you through it. So you need to make your own rational function that has the following characteristics. Crosses the x-axis at 2 and 4. So think about where that would show up in your rational function. And what kind of a rational function would result in 2 x-intercepts at 2 and 4? So start by writing that. So let's start, we could say this, but I want your answers. I don't want to give you the answers here. So say r of x equals, so where would that appear, Katarina? Okay, and what would it look like?
X minus 2x, at x plus minus 4.
Good. How do you know that, Katarina?
Because they're roots.
Yeah, and how do you get the zeros of a rational function? You set the
Numerator to 0.
Yeah, so setting the numerator equal to 0, wouldn't you get these two answers, 2 and 4? Wouldn't you guys agree? If this was your numerator and you set it equal to 0, you get 2 and 4. So we're working backwards now. Okay? Second part, there's a hole at -1. What indicates a hole? What in your rational function? Okay? What do you mean? Sorry, explain yourself, because maybe you're saying something else. Okay, next one, maybe. Erickson.
Degree of the numerator is
Thank you.
the degree of the numerator is less than.
When it's less, that's a horizontal asymptote. That's a hole. Yeah, when the factors cancel. What factor would give you an x value of -1? What would the factor be? If you solved it and set it equal to 0 and you get negative 1 as your answer, what factor gave you that? Like Katarina did it a minute ago. For 2 and 4, she was negative 2 and negative 4. So what factor would give you that? Give me the factor. X plus 1. So put x plus 1 up top and down below. That means there's a hole. Where's the hole now? At negative 1. At negative 1. Okay? Part 3. Part 3. Nick, I think you want to do part 3.
There are two vertical asymptotes as equals negative 5 and 6.
So it would be like,
Good?
I don't know, it would be sandwiched in between.
Good in the graph, but in the equation, where would they show up? Where do you get the vertical asymptotes from? In the equation. That's right. You're right. They would be sandwiched in between. Where do you get the vertical asymptotes usually? This is the hole. These are the roots. So what would go here then? If these are the asymptotes, what would go here?
Negative 5 and 6.
Be careful.
5, 6 plus 6. Or x plus 6.
This is when, that's right. I'm stepping you through it. This is when you set it equal to 0 and solve. So what factor, when set equal to 0 and solved, gives you x equals negative 5?
5.
Good. So it's x plus 5, right?
X plus 5.
And?
And x minus 6.
Good. There you go. That's all you're doing there, okay? So remember, vertical asymptotes come from the denominator equal to 0. So when you see that there's vertical asymptotes, put those factors in the denominator. So we're working backwards. Final step. This is the tough one. There's a horizontal asymptote at 3. What gives you a horizontal asymptote? What gives you a horizontal asymptote? If the what? Make a statement.
The coefficient is for the numerator is larger than the denominator.
Okay, good. But before that, you look at the degrees, right? So what would the degrees have to be?
X 4.
When you have a horizontal asymptote at y equals some number, remember the degrees are the same because you take the ratio of the leading coefficients. When the horizontal asymptote is y equals 0, when the horizontal asymptote is y equals 0, at that point in time, we know that the degree of the numerator is less than the degree of the denominator. The third case is a slant asymptote. So because you have a horizontal asymptote at some number, you must fall into this case. That's the only time you're going to have y equals some number as a horizontal asymptote. But that's obvious that we have this case. Because look at the equation. Isn't it both x cubed? They're both third degree. So what can you do in the very front so that you have some leading coefficients? 6 over 2? Or just... Yeah, I mean, but any answer is possible there. You could put 12 over 4. You could put 300 over 100, right? As long as it reduces to 3 over 1. Because that is the horizontal asymptote. Okay? That makes sense?
Then you can multiply all that out.
No, I would leave it. I would multiply it out. You could if you want. I think I did, but I don't think I have to. Yeah, I did. But don't worry. Okay? Take a look at the graph of it, please. Take a look at the graph of it. Make sure everything makes sense as to what we just said. So, vertical asymptote at negative 5 and positive 6. Horizontal asymptote at 3. X-intercepts, what were they again? I can't really tell on the graph. 2 and 4? 2 and 4? A hole at negative 2 or negative 1? I can't see. Negative 1. Okay? So our graph does match up. It does indeed match up. Okay? I didn't plot points and stuff because I just used the calculator to graph there. But again, you're going backwards there. You're going backwards. So we're going to go on to the next page and take a look at those exercises now. It's A there, right? Okay, start the first one. Go ahead.